This map shows us exactly where we are in the curriculum. Having mastered backpropagation, we can now apply it to the deep learning category, specifically Algorithm 37, Convolutional Neural Networks. We are facing a massive engineering challenge: how to teach a machine to translate a raw grid of pixels into edges, shapes, and objects without the underlying math overwhelming the hardware. The difficulty lies in the logistics of the data. Machine vision requires processing dense, multidimensional grids without triggering a complete computational collapse. To see that collapse in action, imagine feeding a modest 100 by 100 pixel image into a standard neural network. To process it, the network must first flatten that two-dimensional grid into a single line of 10,000 individual pixels. In this fully connected layout, every pixel wires to every single neuron in the next layer. This means one neuron requires 10,000 unique weights. Scaling this to a functional model results in millions of parameters for a single tiny image. This method also ignores the physical reality of an image. By stretching the grid into a flat line, the network loses the spatial context, the fact that nearby pixels share meaning and belong to the same object. Traditional dense networks are mathematically blind to spatial geometry. They are too slow to be practical and too simple to be accurate, which forced researchers to look for a different architecture. In 1980, Kunihiko Fukushima proposed the neocognitron. Inspired by the mammalian visual cortex, it used alternating layers to detect features, but it lacked an efficient way to learn from its mistakes. The solution arrived in 1989 at AT&T Bell Labs, when Jan LeCun successfully applied the backpropagation algorithm to this layered convolutional structure. This architecture solved a concrete industrial problem, teaching machines to automatically read the handwritten zip codes on U.S. Postal Service envelopes and the digits on bank checks. The model reached its full potential in 2012. Using GPUs to scale the architecture over 1 million images, AlexNet halved the error rate of its nearest competitor in the ImageNet challenge. These real-world constraints, speed, accuracy, and data volume, eventually replaced brute force calculation with an elegant, biologically inspired mathematical structure. The core mechanic is simple. A small, learnable filter slides across the image. Hovering over a patch, it performs element-wise multiplication with the pixel values. Those 9 products are summed into a single number and placed into a new grid called a feature map. We can verify the logic here. In this secondary example, the filter matrix and the padded input region sum up to a specific value of 7 in the resulting map. This process establishes the axiom of local connectivity. Because neurons only analyze a tiny, contiguous patch of pixels at once, they preserve the spatial relationships of the original image. It also enables weight sharing. The exact same 3x3 filter is dragged across every position of the image, which drastically reduces the number of parameters the computer must store. By combining local connectivity and weight sharing, the network collapses millions of required parameters down to a handful, fulfilling the efficiency imperative. The architecture moves left to right. Raw pixels pass through specialized processing blocks toward a final classification. After convolution, the ReLU function zeroes out negative values, adding nonlinearity. Then, max pooling keeps the strongest signal in each region, shrinking data volume for the next layer. Stacking these blocks creates a hierarchy. Early layers detect simple edges. Deeper layers assemble those edges into complex shapes, textures, and eventually recognizable objects. This repeated structure of convolving and pooling is the engine. It translates raw, chaotic pixel data into a structured, abstract understanding of the visual world. The elegance of the system relies on these 3 pillars: local filters, shared weights, and a deep feature hierarchy. However, a 3x3 filter is just a grid of meaningless numbers until the system learns what those numbers should be. These edge detectors and shape finders are not designed by hand. The network learns them organically through training and backpropagation. To see how these weights are optimized and how this complex architecture is built, with just a few lines of logic, we have to look directly at the code. The biological inspiration and the calculus we just explored don't live in the abstract. In the packed repository for 50 algorithms, that entire theory collapses into a few explicit lines of Python. We start by defining a Keras sequential model. This builds a linear stack of computational layers, directly mirroring the hierarchical structure of the mammalian visual cortex. Before the network can learn, it needs raw data. We set the input shape to a 28 by 28 pixel grid. That is the exact physical dimension of a standard MNIST handwritten digit, serving as our starting tensor. The top-to-bottom sequence of this code isn't simply organized for developers to read. It dictates the exact physical path an image takes to become a classified object. This diagram illustrates the convolutional layer. We create 32 distinct 3x3 filters, acting as initial edge detectors. The code forces each filter to slide across the image, performing element-wise multiplication and summing the results into a new feature map. Next is the pooling process. A max pooling 2D layer with a 2x2 window shrinks spatial resolution by a factor of 4. By selecting only the maximum value in each window, the network holds on to the sharpest features, discarding irrelevant noise. This specific pairing, a convolution layer to find patterns, followed by a pooling layer to compress them, forms the foundational module of modern computer vision. Looking at the full architecture, we stack a second block, doubling the filter count to 64. Because pooling shrunk the map, we have the computational budget to assemble deeper, abstract features. Basic edges combine into corners, textures, and object ponts. Once shapes are identified, a flattened layer rips the data out of its spatial grid, stretching it into a one-dimensional vector. That vector feeds a dense layer with softmax activation. Softmax evaluate these features, generating exactly 10 probabilities for our numerical digits. The journey is one of increasing abstraction. We start with raw pixels, refine them into shapes, and finally collapse them into a single mathematical identity. We finalize the setup with a model compile command. This plugs the architecture into the standard gradient descent and backpropagation loop we've covered previously. The convolutional neural network is the engine driving modern computer vision. By passing images through a deep, layered architecture, it turns raw pixels into recognizable objects. Today, we are going to map exactly where this algorithm thrives and where it fails. Before CNNs, engineers had to manually write code to detect shapes, edges, and corners. Now, the network learns these feature extraction filters entirely on its own. That self-taught detection leads to a major advantage called translation invariance. If the network learns to identify a stop sign in the top left corner of a frame, it will recognize that same pattern if the sign moves to the bottom right. This diagram shows the specific matrix calculation. Combining automated learning with reliable spatial consistency took computer vision out of the laboratory and scaled it up for heavy industrial use. The ability to autonomously map relationships across a structured space makes the convolutional neural network the default tool for grid-based data. This diagram illustrates networks processing complex visual data. These 3D volume blocks represent layers identifying shapes, pedestrians, and tumors. The definition of grid data extends surprisingly far. By converting sound waves into visual, grid-like spectrograms, researchers use CNNs to process and classify complex audio files. The barrier to entry, however, has always been the sheer volume of data required. Training a network from scratch often demands millions of accurately labeled examples. The modern solution is transfer learning. Developers can download a pre-trained network that already knows how to see, freeze its core layers, and then fine-tune the final outputs on a much smaller, custom dataset. If your problem can be mapped onto a grid and a pre-trained model exists, you have unmatched off-the-shelf analytical power at your disposal. That power comes with a deployment invoice. Building and training a custom CNN from the ground up consumes vast amounts of electricity, time, and expensive GPU computing power. Then there is the black box problem. The network can output a highly accurate classification, but it cannot explain its internal logic, creating massive friction when diagnosing a patient or identifying a suspect. Security is also a concern due to adversarial perturbations. A malicious actor can add an invisible layer of digital noise to an image, completely breaking the network's logic and forcing it to confidently misclassify what it sees. The algorithm is also constrained by physical orientation. While it can track an object meeting across the screen, standard CNNs are not naturally scale or rotation invariant. Simply turning an image upside down can confuse the model unless it was specifically trained to handle it. The spatial power of the CNN carries trade-offs: high resource consumption, an inability to explain its logic, and a vulnerability to targeted interference. For software architects, the decision usually comes down to the geometry of the data. If the dataset lacks a spatial or grid-like structure, a CNN is likely the wrong tool for the job. Applying a sweeping visual filter to standard tabular data, like a spreadsheet of customer ages and incomes, wastes computational resources on patterns that do not exist. For those structured rows and columns, algorithms like gradient-boosted trees consistently outperform deep neural networks with a fraction of the setup effort. CNNs are the default starting point for local, spatial patterns, but the mark of a great programmer is matching the architecture to the shape of the data. This cover shows the source text for our breakdown, 50 Algorithms Every Programmer Should Know, written by Imran Ahmad and published by Pact. You can find the book on Amazon and view the full video series catalog over at neuralsca. Which leaves us with one question: what algorithm do you reach for when data stops being a static grid and becomes a continuous, evolving timeline? When data becomes a sequence where past events dictate future outcomes, the network requires a memory, a requirement that leads directly to recurrent neural networks.